A Hilbert space is a vector space which has an inner product which induces a norm with respect to which it is complete. In this video, we study the Hilbert space in an abstract manner. We first review each of these aspects in turn and then show some of the basic properties or general properties of the Hilbert space which can be derived from these conditions. Okay, let's start. First of all, a Hilbert space is a vector space. So that means it is a set with vector addition and scalar multiplication. So let's review that. Let's say H is a Hilbert space. Then if X and Y are its elements, then we have an operation called addition, that is X plus Y, the result of which is an element of the Hilbert space. And of course, this addition is commutative and associative, and there is an identity element called 0, and also for each element there exists its inverse, and so on. And another operation is scalar multiplication. In this case, in this video, we only consider real Hilbert space. So scalars are real numbers. So let's say alpha is any real number and x is any element of the Hilbert space. Then we can multiply alpha with x, which also belongs to the Hilbert space. And of course, we can combine addition and scalar multiplication. For example, if alpha and beta are real numbers and x and y are elements of the Hilbert space, then alpha x plus beta y also belongs to the Hilbert space. So that's what we mean by it is a vector space. Okay, next, a Hilbert space has an inner product. So what is an inner product? An inner product is a bivariate function. Let's rewrite like this, bracket, dot, dot. So these are arguments of the function, which maps a pair of elements of the Hilbert space to a real number, which satisfies the following conditions. Okay, here we assume x, y, z are elements of the Hilbert space, and alpha is a real number. Okay, first, the inner product between x and y plus z can be split into two parts. The inner product between x and y plus the inner product between x and z. And similarly, the inner product between x plus y and z can be split into two parts, the inner product between x and z and y and z. And the second condition, alpha times the inner product between x and y is equal to alpha x times y, or it is also equal to x times alpha y. Here, again, we are considering only real Hilbert space, okay? No complex numbers. And the third condition, the inner product between x1 and y is equal to the inner product between y and x. So that means the inner product is commutative. And the fourth condition, the inner product between x and x, so it's a self-inner product, so to speak, is always greater than or equal to 0. And fifth, if this inner product between x and x is equal to 0, then x is the 0 vector, and vice versa. So the inner product between x and x is equal to 0 if and only if x is the 0 vector. By the way, this 0 vector is, of course, the additive identity element of the Hilbert space, so which is it comes from the property of the vector space. If you recall, in the case of the real vector space, we first defined the inner product between two vectors, x and y, as the sum of the products of their elements, right? Then, so this was the definition in the case of real n-dimensional vector space. Then we derived these properties as a theorem. But here, we don't adopt any concrete definition of the inner product, but instead, we define the inner product any bivariate function from h times h to r such that these conditions are satisfied. Okay, so this is the abstract way of defining the inner product. And anyway, if we have this inner product, it induces a norm. So we can define a norm of the vector x as the square root of the inner product between x and x. However, we can actually define a norm independently of the inner product. In general, a norm is a function from a Hilbert space to the real numbers that satisfies the following conditions. First, it is positive semi-definite. So that is for any vector x, its norm must be greater than or equal to 0. And second, if the norm of x is 0, then that means the vector x itself is the 0 vector, and vice versa. And 3, let's say alpha is a real number, then the norm of alpha x is equal to the absolute value of alpha times the norm of x. And finally, we require the triangle inequality. So x and y are any vectors of the Hilbert space. So the norm of x plus y is less than or equal to the sum of the norms of x and y. So this is triangle inequality. So this was usually, so far it has been proved as a theorem, but here we require as one of the axioms of the norm. In the case of the Hilbert space, we already have an inner product, and using the inner product, we can define the norm as this. And by defining this way, these 4 conditions are automatically satisfied. So it is a norm induced by the inner product. And finally, a Hilbert space must be complete. What this means is that any Cauchy sequence in a Hilbert space is also a convergent sequence. So suppose we have a sequence of vectors in an Hilbert space. Then if this limit n and m both going to infinity, the difference between xn and xm converges to 0, then this means the sequence is a Cauchy sequence. And in a Hilbert space, if a sequence is a Cauchy sequence, then there exists some element in the Hilbert space such that the limit n going to infinity, the difference between xn and this x converges to 0. In other words, the limit of the sequence is x. Xn, so this is in the Hilbert space. And by the way, if a sequence is a convergent sequence, and it is easy to show that it is also a Cauchy sequence. So in a complete space, being a Cauchy sequence and being a convergent sequence, they are equivalent conditions. So to summarize, a Hilbert space is a vector space with an inner product which induces a norm, and with respect to that norm, any Cauchy sequence is a convergent sequence. Okay, Now, let's see some of the general properties of the Hilbert space as defined by these properties. First property is the Cauchy-Schwarz inequality. Cauchy-Schwarz. That is the absolute value of the inner product between x and y is less than or equal to the product of the norms of x and y. The proof of this is just like usual. So let t be any real number, then we have this inequality. 0 is less than or equal to the norm squared of t times x plus y. Okay, so let's expand this. And using the definition of the norm. So we define the norm of x as the square root of the inner product, right? So by using this, we can expand this as t squared, x norm squared, plus, and we are considering only the real Hilbert space here. So this will be 2t, the inner product between x and y norm squared. Okay, so let's consider this as a quadratic form of t. Then the discriminant of this quadratic form should be less than or equal to 0 because it's always greater. This form is always non-negative. So the discriminant is xy squared minus x norm squared times y norm squared. So this should be less than or equal to 0. So from this, it follows this Cauchy-Schwarz inequality. And we are done. And we should note that in this proof, we never used any explicit representation of the vectors or the inner product or the norm. All we used was the definition of the norm as this. So it's an induced norm from the inner product. And general axiomatic properties of the norms or the inner products. That's all we used. Therefore, as long as we have a norm induced by an inner product, this Cauchy-Schwarz inequality holds for any space. Based on the Cauchy-Schwarz inequality, we can prove the continuity of the inner product. By the continuity of the inner product, we mean the following. Suppose we have a sequence of vectors in the Hilbert space, and that converges to x. Then, for any vector y in the Hilbert space, the limit of the inner product between xn and y converges to the inner product between x and y. So this is what we mean by the continuity of the inner product. So let's prove this. By the way, this convergence implies the limit of the difference between xn and x is 0. Okay? So using this, 0 is less than or equal to the difference between the inner products between this one and this one. Okay, so xn, y, we should put this, minus x and y. And this is equal to, by using the property of the inner product, we can combine these two inner products into one inner product. Xn minus x times y. And now we use the Cauchy-Schwarz inequality, so we can split this. So the norm of xn minus x times the norm of y. But this one converges to 0, so this converges to 0 as n goes to infinity. Therefore, this quantity is greater than or equal to 0 and converges to 0. So by the squeeze theorem, this converges to 0. Therefore, this limit holds. The next property is the triangle inequality, which is actually one of the axioms of the norm. So this should hold trivially. And we can also prove this from the Cauchy-Schwarz inequality in our case. But we skip the proof of this one, but we also introduce another version of the triangle inequality, which is this: the difference between the norms of x and y. Its absolute value is less than or equal to the norm of the difference between x and y. So this one, let's prove this. So x norm is equal to x minus y plus y, which is less than or equal to, using the triangle inequality, x minus y norm plus y norm. So from this, we have the norm of x minus the norm of y is less than or equal to x minus y. And by symmetry, we can also prove y minus x less than or equal to y minus x. But this one and this one, they are the same. So therefore, by combining these, we have this second triangle inequality. And by using this, we can prove the continuity of the norm, actually, which can be also proved as a corollary of the continuity of the inner product. But anyway, let's do it. So by the continuity of the norm, we mean this: if xn converges to x, then the norm of xn converges to the norm of x, which seems quite trivial, but anyway, let's prove it. And again, this convergence means the limit of the difference between xn and x converges to 0. So using this, first consider 0 less than or equal to the absolute value of the difference between these. So the norm of xn minus the norm of x. And using the second triangle inequality, this is less than or equal to the norm of the difference between xn and x, which converges to 0 as n goes to infinity. Therefore, this difference converges to 0. Oh, wait a minute. So this should be absolute value here. So therefore, this holds. Okay, next, let's prove again the continuity of the inner product, but here we consider the inner product as a bivariate functions. So for any x and y, xn and yn, these are sequences, and x and y. And if x is the limit of the sequence xn, and y is the limit of the sequence yn, then the limit of the inner product between xn and yn as n goes to infinity converges to the inner product between x and y. Okay, so let's prove this. Okay, so first, 0 is less than or equal to the difference between xn, yn minus xy. Okay, so let's add, subtract the inner product between x and yn here, and add it again. And combine these two and these two. So we have xn minus x times y and plus x times yn minus y. And we can use the triangle inequality for the real numbers to split these two things. So we have the absolute value of the inner product between xn minus x times y plus the absolute value of the inner product between x and yn minus y. Okay, now we can use the Cauchy-Schwarz inequality to both of these terms. So we have xn minus x times y norm and x norm times yn minus y norm, which converges to both of these. This converges to 0 and this converges to 0. So everything converges to 0. Therefore, this thing converges to 0. That means that the inner product is continuous with respect to both of the arguments. And we are done. Finally, let me give the parallelogram law. That is this. The norm squared, x plus y norm squared plus x minus y norm squared is equal to 2 times x norm squared plus 2 times y norm squared. So proving this is just trivial. If you just expand these two norms by using the inner product, then we just get this on the right hand side. But what's important here is that we can do some geometry in the Hilbert space. So if we have two vectors, x and y, then we can make a parallelogram using these vectors. So, and this vector is x plus y. And this vector is x minus y. So the sum of square norm of this and the square norm of this is equal to twice the sum of the square norm of x and square norm of y. So that's what this parallelogram law means. So what's nice about the Hilbert space is that we can do some geometric interpretations of the vectors. Okay, that's all for this video. See you next time. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.